General Relativity, Einstein's masterpiece, describes the universe on grand scales. It provides a framework for understanding how massive objects influence the fabric of space-time, creating the gravitational forces we observe. It predicts the existence of black holes, regions of space-time where gravity is so intense that nothing, not even light, can escape. These cosmic giants are fascinating and mysterious, capturing the imagination of scientists and the public alike. These objects form when massive stars collapse under their own gravity. The process is both violent and beautiful, often resulting in a spectacular supernova explosion before the star's core contracts into a black hole. The mathematics of general relativity tells us that at the heart of a black hole lies a singularity. This is a point where densities become infinite, and our current understanding of physics can no longer describe the conditions. A singularity is a point of infinite density and zero volume. It represents a boundary beyond which the known laws of physics cease to be useful. It is a place where the laws of physics as we know them break down. The very fabric of space-time is distorted beyond recognition, leading to a realm of unknowns. However, the existence of singularities poses a problem. They introduce paradoxes and inconsistencies that challenge our understanding of the universe. They are points where our current understanding of physics fails. Enter the Planck scale. This scale bridges the gap between classical physics and the quantum realm, offering a new perspective on these enigmatic points. This scale, named after the physicist Max Planck, represents the fundamental limits of our current theories. It is a domain where the effects of quantum mechanics become significant, even for gravity. The Planck length, approximately 10 to the minus 35 meters, is the smallest possible unit of distance. It is a scale so minuscule that it defies our everyday experiences and challenges our imagination. The Planck time, around 10 to the minus 43 seconds, is the smallest meaningful unit of time. It represents the briefest moments after the Big Bang, where the universe was in its infancy. At the Planck scale, quantum effects become significant even for gravity. This is where the classical concepts of space-time and gravity merge with the probabilistic nature of quantum mechanics. This is where the concept of Planck-scale Planck stars emerges. These hypothetical objects could provide insights into the nature of singularities and the unification of general relativity with quantum mechanics, offering a glimpse into the fundamental workings of our universe. Planck-scale Planck stars arise as stabilized remnants of quantum corrections during collapse at densities approaching the Planck scale. Loop quantum gravity, or LQG, is a leading contender for a quantum theory of gravity. It attempts to reconcile general relativity with quantum mechanics. LQG suggests that space-time itself is not continuous, but is woven from tiny loops. These loops have a minimum size, the Planck length. This discrete nature of space-time has profound implications for the fate of collapsing stars. In LQG, as matter collapses under gravity, it eventually reaches the Planck density. This density corresponds to packing one Planck mass into a Planck volume. At this point, the quantum nature of space-time becomes crucial. The quantum foam is a term used to describe the fluctuating nature of space-time at the Planck scale. Imagine the fabric of space-time constantly bubbling and churning. These fluctuations, though incredibly tiny, become significant at extremely high densities. In the context of a collapsing star, the quantum foam acts as a barrier against further compression. When the collapsing core reaches the Planck density, it encounters the resistance of the quantum foam. This resistance arises from the fundamental discreteness of space-time. The core cannot be compressed any further, preventing the formation of a singularity. Section 4. Symmetry breaking and the birth of Planck stars. As the collapsing core encounters the quantum foam, a fascinating phenomenon occurs. Symmetry breaking. In physics, symmetry refers to a system's invariance under certain transformations. For instance, a sphere is symmetrical because it looks the same from all directions. In the early universe, the fundamental forces of nature were unified. As the universe cooled and expanded, these forces separated in a process known as symmetry breaking. Similarly, at the Planck scale, the symmetry of space-time itself breaks down. This breakdown leads to the formation of a Planck star. The immense energy density within the collapsing core, now unable to form a singularity, gives rise to a new object governed by quantum gravity. Section 5. Quantum tunneling, escaping the black hole. Unlike classical black holes, which are inescapable prisons for anything that crosses their event horizon, Planck stars offer a potential escape route: quantum tunneling. Quantum tunneling is a phenomenon where particles can pass through energy barriers that classical physics deems insurmountable. Imagine rolling a ball up a hill. Classically, if the ball doesn't have enough energy to reach the top, it will roll back down. In the quantum world, there's a chance the ball could tunnel through the hill and appear on the other side. In Planck stars, the quantum foam surrounding the ultra-dense core provides a similar energy barrier. While matter cannot escape classically, quantum tunneling allows particles to tunnel through the quantum foam and escape the Planck star's gravitational pull. This process also releases energy, potentially giving rise to observable signatures. To understand this better, let's compare black holes and Planck stars. Black holes are regions of space-time where gravity is so strong that nothing, not even light, can escape from them. They are formed when massive stars collapse under their own gravity. On the other hand, Planck stars are hypothetical objects that form when a black hole's core reaches a critical density, causing quantum effects to counteract the gravitational collapse. These quantum effects create an energy barrier, similar to the hill in our earlier analogy, which particles can tunnel through. This tunneling process is not instantaneous. It takes time for particles to escape, and the rate of tunneling depends on the properties of the quantum foam and the energy of the particles. As particles escape, they carry away energy, which can be detected as radiation or other observable phenomena. These signatures could provide crucial evidence for the existence of Planck stars and help us understand the nature of quantum gravity. By studying these energy releases, scientists hope to unlock new insights into the fundamental laws of physics and the true nature of our universe. The concept of quantum tunneling in Planck stars not only challenges our understanding of black holes, but also opens up new possibilities for exploring the mysteries of the cosmos. As we continue to delve into these phenomena, we may one day find answers to some of the most profound questions about the universe and our place within it. The journey to understand black holes and Planck stars is just beginning, and the discoveries we make along the way will undoubtedly reshape our understanding of the cosmos. Stay tuned as we continue to explore the fascinating world of quantum physics and the mysteries of the universe. The adventure is far from over, and the universe still holds many secrets waiting to be uncovered. Section 6. Planck. Stars in the early universe. Seeds of structure. The extreme conditions of the very early universe, just fractions of a second after the Big Bang, may have provided ideal environments for Planck star formation. During this incredibly brief period, the universe was a hot, dense soup of particles and energy, undergoing rapid expansion and cooling. Quantum fluctuations in the primordial energy density could have created regions dense enough to collapse into Planck stars. These fluctuations, tiny variations in the density of matter and energy, were crucial in shaping the universe's large-scale structure. These Planck stars, unlike their stellar mass counterparts, would have been incredibly tiny, yet incredibly massive. Imagine objects smaller than an atom, but with masses comparable to a mountain. Their extreme density and gravitational pull would have made them unique cosmic entities. The formation and subsequent evaporation of these primordial Planck stars could have played a crucial role in the early universe. As they formed, they would have influenced the surrounding matter, and their eventual evaporation could have released significant amounts of energy and particles back into the cosmos. They might have seeded the formation of larger structures, contributing to the distribution of matter that eventually led to galaxies and galaxy clusters. These tiny yet powerful objects could have acted as the initial gravitational wells, around which matter began to coalesce, forming the first building blocks of the cosmic web. Moreover, the remnants of these evaporated Planck stars could still linger in the universe today, potentially offering a new perspective on dark matter. These remnants, though no longer active, might still exert gravitational influence, contributing to the mysterious dark matter that makes up a significant portion of the universe's mass. Section 7. Detecting the undetectable, searching for Planck star signatures. While Planck stars offer a compelling alternative to singularities, their existence remains theoretical. Detecting these incredibly small and distant objects poses a significant challenge. However, physicists are actively exploring potential observational signatures that could provide evidence for their existence. One promising avenue is the detection of gravitational waves. The formation and evaporation of Planck stars should produce characteristic gravitational wave signals, distinct from those produced by black hole mergers. These signals, though faint, might be detectable by future generations of gravitational wave observatories. Additionally, the energy released during the quantum tunneling process could manifest as bursts of gamma rays. Observing such bursts from the early universe would provide tantalizing hints of Planck star activity.